Students, in continuation with the previous video, in this video also we will be drawing Bode plots for some basic transfer functions. So in the previous video we have drawn a Bode plot for two functions, that is g of s is equal to a constant k and g of s is equal to k by s. So now let us draw for g of s is equal to k into s. So the first step is you have to substitute for s for j omega. So you got it as k into j omega. The magnitude of j omega is omega and phase of j omega is 90 degree. Okay. So ultimately the magnitude part is k into omega and phase part is 90 degree. So when you split and write, phase is 90 degree and magnitude is in decibels is 20 log of k omega. So now let us draw phase versus frequency. Phase is irrespective of frequency, it is 90 degree. So irrespective of frequency, for any frequency, the phase is at plus 90 degree. If the 0 degree curve is here, 90 degree is drawn here. Okay. For magnitude, the magnitude will be varying with respect to different chosen frequencies. We have chosen three different frequencies, okay, in terms of omega. So that, in terms of k, so that k gets cancelled and you will get a constant value for magnitude, okay. So the three chosen frequencies are zero point 0.1 by k, 1 by k and 10 by k. So the magnitudes you obtain for these three frequencies are minus 20 decibels, 0 decibels and plus 20 decibels. Okay. So if you look at this curve, you have a slope. Am I right? The slope is, you can see that it is plus 20 dB. At this point, you have it as 0 decibels and at this point you have it as 20 decibels. So it is for 10 times increase in the frequency, the slope is or the magnitude increases by 20. Okay. So the slope of this curve is 20 decibels per decade. DECADE, decade. Okay. 10 times increase in the frequency, you have magnitude to be increasing from 0 to 20. So the inference is yes in the numerator. Yes in the numerator will contribute to 20 decibels of slope. Yes in the denominator. In the previous video we have seen that S in the denominator contributed to minus 20 dB for the magnitude curve. Okay. So that is the inference. So for the next transfer function g of s is equal to 1 divided by 1 plus s into t. So already this term is in the standard format, 1 plus s into constant. This constant is called as the time period. The inverse of, that is the reciprocal of this time constant, will be your corner frequency omega. Here you have only one t, so you have got only one corner frequency. At the end of this particular slide you will be knowing what is the inference of this corner frequency. Okay. So the first job is s should be replaced by j omega. You got it as 1 divided by 1 plus j omega t. Please find the magnitude of this term and phase of this term. The magnitude is equal to square root of 1 square plus omega square t square, and phase is tan inverse of omega t by 1. Okay. So when you write phase separately, since the phase is in the this term is in the denominator, phase is minus tan inverse of omega t. Okay. And you have to write the this particular magnitude term in terms of decibels. So apply 20 log to it. Okay. When you apply 20 log of 1 minus 20 log of this term. So 20 log of 1 is 0 decibels. So you will have 0. So I have not written here 0. So no need of writing 0. So it is minus 20 log of square root of 1 plus omega square t square. So this is magnitude and this is phase. Okay. Now try to draw the curve between a versus omega and phi versus omega. So here is a curve. If you draw the curve, you will get a curve like this. For you have to choose different values of frequency and get the value of phi. Okay, phi is nothing but phase, and then if you plot, you will get a curve like this. Okay, for magnitude also, after this corner frequency, you will have a slope of minus 20 dB. That is what is the inference from this particular graph. If you draw the graph, you will get it like this. This is the corner frequency. What was the corner frequency? 1 by t. After the corner frequency, okay, you will get a slope of minus 20 dB. See, you can just remember it like this, because S is in the denominator, it contributes minus 20 decibels. That too after the corner frequency. S is not individual. S is along with a constant plus 1. Am I right? So after the corner frequency, it contributes minus 20 decibels. So that's the inference from this graph. Uh, you can just think of a graph with g of s is equal to 1 plus s into t. That is a 1 plus s into t in the numerator. Can you just think of it? So by the time you think, here is the graph. Okay. The same thing done here. S is equal to j omega. You got this term. This is the magnitude and this is the phase. So magnitude now written in terms of decibels. Phase, try to draw phi versus omega, log omega, and a versus omega. Okay. After the corner frequency, okay, 1 by t, 1 by, this is s into a constant. Here also the corner frequency is 1 by t. After this corner frequency, after this corner frequency, at this conference, omega c is equal to 1 by t is the corner frequency. After this corner frequency, you can see that the slope is plus 20. The slope is plus 20 dB because this s term is in the numerator. So now you are able to correlate. S in the denominator contributed minus 20. S in the numerator contributed plus 20. Since this term is having a corner frequency, this happens after the corner frequency. Okay. The earlier transfer function also had a corner frequency. So after that corner frequency, you are having a slope of minus 20 dB. Okay. So correlate everything, all the Bode plots that we have seen so far. And as I said, we will also look into a function which is having a quadratic function in the denominator. Okay. Suppose you have a quadratic function in the denominator like this. Okay, that is s square term is there. As usual, you can replace s with j omega. Okay, s is equal to j omega. So instead of this s, you will get j omega. Once you substitute s is equal to j omega, when you rearrange it, you will have a real part plus j into imaginary part. Real part plus j into imaginary part. Okay. Then you can find the magnitude. After finding the magnitude, you can apply 20 log. And once there is a real part and imaginary part, the phase is tan inverse of b by a. Since it is in the denominator, it is minus. Okay. So now you can draw between a versus omega and phi versus omega. This is given only just for demonstration purpose. Okay. So since there is a variable tau damping ratio here, for different values of tau, you can see how your curve varies. Okay. You can see how your curve varies. This is your magnitude curve and this is your phase curve. And similarly, in the next slide, we will be seeing a quadratic function in the numerator. Okay. See, actually, you have to compute the magnitude and phase and try to plot it. But since this is just for demonstration purpose, we are straightly giving the graph. So this is another function where the quadratic function is in the numerator. Okay. So you have natural frequency, you have damping ratio, you have s. Instead of s, you have to substitute j omega. You get a real part. These two forms the real part, and this one forms the imaginary part. And you have to find the magnitude. Okay, so you have that is square root of a square plus b square as the magnitude. You apply 20 log. The phase is tan inverse of b by a. After getting these two, you vary the frequencies. For different values of frequency, you will get phi. Okay. So now here the curves are shown for different tau, because tau is also a parameter in the right hand side. So they have given that. So here we are going to draw a rough sketch of Bode plot for this given function from the knowledge that we have gained in the previous slides. Okay. So here I will take four different terms. One is 1k by s square. Another one is 1 plus s t1 the whole square. Another one is 1 divided by 1 plus s into t2. Another term will be 1 divided by 1 plus s into t3. Let us assume that the cutoff frequencies are in this order. That is this cutoff frequency, that is 1 by t1 is one cutoff frequency, 1 by t2 is another cutoff frequency, and 1 by t3 is another cutoff frequency. Let us have it in the increasing order like this. Omega c1 comes first, and omega c3 comes next, and omega c2 is the largest cutoff frequency. Let us assume this order, and now let us start. For k by s square, since it is s square in the denominator, s in the denominator will contribute minus 20 decibels. Now it is s square, it will contribute minus 40 decibels. So when you draw for k by s square, you will have a curve like this, minus 40 decibels. Okay, contributing minus 40 decibels per decade. Okay, this is the first curve. Then if I draw it for the first cutoff frequency, which comes the first cutoff frequency, that is omega c1, which term it is 1 plus s into t1 the whole square. Okay, here s in the numerator, but it is squared. Okay, it comes as a whole squared, so that means plus 40 dB, plus 40 dB after the cutoff frequency 1 by t1. So after the cutoff frequency, that is omega c1, see here, after the cutoff frequency omega c1, it contributes plus 40 decibels. Okay, this is for the second term. So our third term is 1 by 1 plus s into t3. Okay, so this will contribute minus 20 decibels because s is in the denominator, but after the cutoff frequency 1 by t3, that is omega c3. Okay, so omega c3 comes here. After this cutoff frequency you will have minus 20 decibels. Okay, then the last term is 1 divided by 1 plus s into t2. Okay, so for this the cutoff frequency is 1 by t2, that is omega c2. So after this omega c2, it will contribute minus 20 decibels because s is in the denominator. So these four different curves, you can combine it into one. Okay, and then get the rough sketch of magnitude plot for this particular transfer function. So start from here, it is starting is minus 40 decibels. Okay, after this particular cutoff frequency, you can see that this curve continues to be at minus 40, whereas you have another contribution of plus 40. So minus 40 term with the plus 40 contribution, it becomes 0 dB. Okay, so this line will be from this cutoff frequency to this cutoff frequency, it will be 0 decibels. Now the curve is continuing with what slope? 0 decibels dBs per decade slope. Okay, the slope is 0. That means there is no slope. You will have a constant line. Okay, the curve is continuing. After this cutoff frequency omega c3, there is a term coming in with a slope of minus 20 dB. So your graph also will take a curve or a slope of minus 20 decibels. It continues till this point. After this cutoff frequency omega c2, okay, already the graph is continuing with minus 20 decibels, and now you have a contribution of again another minus 20. Okay, so it is minus 20 into minus 20 plus minus 20, it is minus 40 decibels. So the curve will continue with minus 40 decibels per decade slope. Okay, so this is your final Bode plot. This particular information will be very useful for you if you're going to write gate exams, because they'll give you some rough sketch of magnitude graphs, and they'll give you tell you to choose which transfer function matches for the given graph. Okay, so you can just do this and find out. So I repeat it. So the curve starts with minus 40 decibels. When it crosses this particular frequency, it meets plus 40 dB fellow. So both cancel out and the curve continues at 0 decibels. After this cutoff frequency, there will be a slope of minus 20 decibels. Okay. After this omega C2 cutoff frequency, already it is traveling with minus 20 dB. Now minus 20 again adds to it. Okay, it will be minus 40 decibels per decade. So this way also you can draw, but of course we are not going to follow this kind of thing. We will follow magnitude versus omega and phase versus omega, computing separately and drawing it. So those things will be dealt in the next video. Okay. So students, please be ready with the semi-log graph sheet for the next session.